Good afternoon. So I'm going to talk about the Sun and its role as our nearest star. And at a distance of, only 150 million kilometers away from us, it dominates life here on Earth. It dictates day and night. It's the source of all our energy, all our heat and light. Not just the Earth, but every object within the solar system. And it is a truly enormous object. Here's the Sun. Now, I can tell you it's 1.4 million kilometers across. Whoop, interesting echo. And if I then just show you the Earth to scale, okay, for those of you in the back who can't quite see it, there it is. You need well over 1 million Earths to fit inside the Sun. So it's not only large in terms of its size, it's also enormous in terms of its mass. It's 330,000 times more massive than the Earth. Or to put it in another way, if you added up all the mass in all the planets and the moons and the comets and the asteroids and the dwarf planets, every other object in the solar system, the Sun is still 700 times more massive. So that is why it sits at the center of our solar system, and its gravity dominates. That's where everything else goes in orbit around the Sun. So you have this object sitting at the center of our solar system, and it exerts a profound influence on the Earth. As I say, it's the source of all our heat, our light, all our energy. It can also be a danger to us. And perhaps in some ways this is unique amongst astronomical topics of research, is the Sun is something that can have a profound influence on our day-to-day life. And variations in that Sun, as you'll hear, some of the radiation, some of the plasma it can send the way of Earth, can be inherently dangerous for us and the sort of society that we build up now. So observing the Sun has important relevance for our everyday life. So we can observe the Sun in its own right, try to forecast what it's going to do, how it's going to affect us. But not just that, because it is our nearest star, it gives us a sense of being able to observe at first hand the processes that we think are operating in other stars, actually trying to tie down what's going on in these far more remote objects, how we test the internal structure of stars, our theories of how stars are born, live, and die. So we've got, this is our own close laboratory for all these stellar processes that are going on. Now, the Sun is made of gas. You can see from this picture, so this is taken through certain light. I mean, I've talked about it being 1.4 million kilometers wide, so it's 1 million times the volume of Earth, but it's only 330,000 times more massive than the Earth. This means its average density is much less. It's not mostly made out of rock like Earth. It is a gaseous object, and it's a very hot gaseous object. But there's substantial variations within that gas. The outer surface that you see here is a temperature of about 5,780 degrees above absolute zero, so the surface is very hot. But it gets hotter as you go in towards the center. And right at the core, you're reaching temperatures of about 15.7 million degrees above absolute zero. So you have an enormous change in temperature. You also have an enormous change in density. It may be quite comparatively light, especially those outer layers of the Sun. But as you go towards the center, you've got all the way to the outer layer, squeezing the center, compressing it. And by the time you get to the center here, you've got densities at about 150 grams per centimeter cubed. That's of the order of 13 times more dense than lead. So again, vast variations, both temperature, getting hotter towards the center, and density. And the key component of the Sun is its core. And this is where you've probably got about half the mass of the Sun squashed into about 2% of the volume. And I've depicted it here in this sort of cutaway diagram as blue, just to represent it being hotter. Of course, there isn't a sharp, edge to the core. It's just schematic. And the rest of the Sun, as I say, is gaseous. But it's not just gaseous. This matter is so hot that it goes beyond gas. And we have the sort of fourth state of matter, if you like, which is plasma. And plasma is where the gas is so hot that the atoms have been stripped of their electrons. And so the whole of the particles in the gas are electrically charged. So you have an electrically charged plasma. And this is why the sun is of so much interest, not just in its own right and as a representative of more distant stars. It is our nearby laboratory for looking how electric charges and how magnetic fields interact with each other at quite extreme temperatures. The sun is the most magnetic object within the solar system. And it has a strong magnetic field. And so the fact that it's mostly charged gas then means the two are very tied together. So to explain, if you have a charged particle, it is constrained to follow along magnetic field lines. So the magnetic field lines influence how the charged gas moves, the charged plasma moves. And the sun, as I say, is a very strong magnetic field. If you could look at how the magnetic field lines come out of the surface, it would look like the Earth's magnetic field, like your standard bar magnet. It's got a north pole and a south pole with big loops of magnetic field lines joining the two. So obviously, that inherent magnetic field within the sun influences how the plasma changes. But then you have a knock-on effect in that moving electric charges generate further magnetic fields. And they kind of amplify and feed back any seed magnetic field. And so you have this thing where the motion of the magnetic field affects how the plasma moves, but then how the plasma moves also affects the magnetic field. And the plasma will trap and move the magnetic field with it. And so the two are inherently intertwined and interconnected. And so, for example, here you have a picture of some of the localized magnetic structures on the sun that have pulled some of that plasma out of the sun that loops along and traces along these magnetic field lines. And you're going to see how the magnetic field of the sun and variations near the surface are incredibly important for a lot of the activity and the manifestations of behavior we see and observe on the sun. Now, obviously, it's something that we've been observing for millennia. And the earliest recordings of observations of things that are curious about the sun date back to ancient Chinese astrologers and astronomers, 800 BC. But the sun doesn't vary that much to the unaided eye. Sometimes, and I have to tell you for health and safety reasons, this is highly not recommended, but if it's behind a bank of fog or at sunrise and sunset and the light from the sun is dimmed, you can see structures on the sun with the unaided eye. And there have been records, so you can see in this picture, there are some dark patches, some dark blobs on the surface of the sun. And these were occasionally noted when these were visible to the unaided eye, when, as I say, the light of the sun was slightly obscured. The first actual recording we have, or drawing of one of these, dates back to 1128, when the English monk, John of Worcester, recorded in December 1128, seeing two black sort of spots against the sun that lasted all day. And this is his sketch of this, this apparition. And he was thinking of them as something moving in front of the sun. He didn't associate them with the sun, itself. And curiously, in Korean astronomy records, a week later, or if you can read Korean, this is what I'm assured it says in the highlighted text. I will not profess to be an expert in Korean. But there were records of a red vapor filling the sky, which we would interpret now that, after this appearance of this sunspot on the surface was recorded, there were sightings of aurorae, unusual at those latitudes. So again, that's just prefacing what's going to come later about the Sun-Earth connection. But real advances in understanding features or changes on the sun didn't come really until the advent of the astronomical telescope. Here are John Harriot's drawings of sunspots, marks on the surface of the sun. Of course, they were studied much more extensively a little bit later by Galileo, who took detailed pictures of sunspots, drawing their structures and also mapping about how they change from one day to the next. I suspect such observations are a lot easier from Italy than they are from Britain. And there was a lot of debate about in the early 17th century, were these structures in the atmosphere, on the disk of the sun, or were they things intervening between us and the sun? And this wasn't really reconciled till, agreement by about 1630 that this was something inherent to the sun. And then just as telescopic astronomy was getting going, the sun then goes quiet for about 75 years, with not a sunspot in sight. And so there's a kind of big lull in solar astronomy, and it doesn't really begin to pick up and change until the 19th century. By then, you've got John Herschel doing observations of sunspots, and I think it's a drawing from South Africa where he's showing the structures. You've got a dark center to this sunspot, this dark area in the sun, and it's got a stripy kind of penumbra, we call it, a ring around it. And by the middle of the 19th century, there's a very brilliant solar astronomer, British solar astronomer called Richard Carrington, who observed the day-to-day changes on the sun. He not only just mapped the changes in sunspots and how they rotate around the sun, he showed that the sun, different parts of the sun rotate at different speeds by tracking the motion of the sunspots. And so you find that at the poles, it takes about 10 days longer to rotate once round than it does at the equator. The center of the sun is spinning faster than at the poles. So this is telling you it's not a solid body. It really is a gaseous body. But there was an amazing breakthrough when he was observing the sunspot, a very active sunspot region on the sun in 1859. On the 1st of September, in fact, here's a bit from his paper. So he projects the image of the sun onto a sort of surface, and he's making detailed observations of the dark patches, the sunspot regions on the solar surface. When he sees a brilliant flash of white light, it's so bright, his first assumption is that there's a hole somewhere in the apparatus that's letting direct sunlight onto his image. And he moves the telescope, and he finds that the bright flash of light moves with it. It's associated with the image of the sun. It's not a leak in the telescope. He realizes he's observing something really, really important, and he goes off temporarily to try and find a second observer, a second witness to this occurrence. And when he comes back 2 minutes later, this bright light is already fading. And here's his drawing of the sunspot region. And these two regions he's marked A and B. That's where there's that bright flash of light. So actually observing this happening, this change on the surface of the sun that only lasts a couple of minutes, is the first step. But it's connecting that to events on the Earth that happened straight afterwards that was the crucial thing about showing how what goes on at the sun affects us here on Earth. Because within 17 hours of Carrington making this observation, there were widespread aurorae all around the globe. Fabulous aurorae, much further south than you'd normally see them, down as far as Cuba and Hawaii. Apparently these aurorae were so bright that in places in Central America, it is alleged you could read newspapers by them. Magnetic recordings of the Earth's magnetic field registered a huge storm, huge variations. Something was really shaking the Earth's magnetosphere. And there were other reports from telegraph offices, because of course telegraphs have been running for about 20 years by the time, of strange happenings along the telegraph lines. First of all, there was a surge of current along them, which set fire to some telegraph offices, even shocked some poor operators within the telegraph offices. There are records of people who, having detached the batteries at each end of the telegraph line, found it worked much better without them. That there was this ghost current that was just carried on transmitting the messages. And all of these happenings were noted because they had all happened the week before. But the fact that it happened again, and just after Carrington saw this bright flash of white light, made the first association that what happened on the sun was influencing what happened on the Earth. So you get to this point where you're beginning to understand how important the sun is, but there is still a fundamental problem about knowing kind of how the sun shines. What is the source of all this energy? And even by the early 20th century, this was not determined. People had gone through various ideas. It can't be chemical burning, because there isn't enough mass in the sun to make it shine for longer than 10,000 years. And we obviously knew from sedimentary geology that the Earth had existed for several 100 million, if not a few billion years by then. Other ideas, whether it was the squeezing of the outer layers causing the compression in the middle, causing the gas to heat up that might, give it that energy, cause it to radiate this heat and light. But again, that couldn't sustain it for anywhere near the age of the Earth at the time, even once you incorporated the process of radioactive heating. The difference came when Einstein's special theory of relativity came out in 1905, and Sir Arthur Eddington realized the importance of nuclear fusion as a potential source for the sun. And just to be absolutely clear about the power, the kind of power that's generated by the sun is 400 septillion watts. And if you don't know what 400 septillion watts look like, here you are. Plenty of zeros. And the principle of nuclear fusion is, well, if you're doing chemical burning, if you're doing chemical processes, you're more or less rearranging the electrons around the outside of the nucleus. So let me just be quite clear. Here's your atomic nucleus. At the center, you've got a whole bundle of protons, which are the positively charged particles, the neutrons, which are the neutral particles. They're all held together quite tightly. And then there's a cloud of negatively charged electrons that flies around them. And what determines which chemical element you have is how many protons you have in the nucleus. So chemical burning rearranges the electrons between different atoms. However, nuclear processes changes the number of protons in the nucleus. It changes the chemical element. And, you know, it's a much more difficult process to do because the force that binds the nucleus together is far stronger than the one that ties the electrons to the nucleus. And so if you are going to do nuclear processes, rearrange and swap neutrons and protons within the nucleus, first of all, this force operates over very small distances. So you have to get the particles close together. You have to get these nuclei close together. Of course, both nuclei of hydrogen atoms, helium atoms, in fact, all atoms are positively charged. You put them close together, there's a strong electrostatic repulsion. So you need to put them together at high speed so they can overcome that repulsion and get close enough together for the nuclear processes to happen. And this can only happen in the core of the sun. And that's what Eddington realized, that the conditions there were so hot, well over 10 million degrees, so dense, 13 times the density of lead, that things were moving and these nuclear processes could happen. And so what the net result is, I mean, there's a long chain of events, and in the core of the sun, you're changing 4 hydrogen nuclei, so just protons, to 1 helium nucleus, and you do it in a number of steps. And it's called the proton-proton chain, and there are 3 steps. But the net result is that this helium nucleus is in fact slightly lighter than the protons you input. There's been a net tiny loss of mass. And here's our token equation for the day, equals mc squared. C is the speed of light. So a tiny bit of mass, m in this equation, generates a huge amount of energy. Excuse me. And so just that tiny loss of mass is what perpetuates the energy of the sun. And to keep that rate of power being issued out from the sun, you need to burn the mass of the sun, hydrogen in the sun, at a rate of 600 billion kilograms every second. Now that sounds a huge amount, but there's plenty of mass in the sun, right? It's a very efficient process. We reckon that it's been going for about sort of 5 billion years. There's plenty of mass in the sun to sustain this for another 6 billion years. And anybody who's very good at mental maths may already be saying, no, there's more mass than that. You've got to remember, this is only going in the core. You can't use the whole mass of the sun. It's just like that central region where you've got the good enough temperatures and densities for the nuclear process to occur. So this was the breakthrough, the idea of nuclear fusion. You're turning hydrogen to helium at the core of the sun. The energy is generated in the center. Some of it is carried away as neutrinos. Most of it is issued as radiation. This radiation, as it passes through the outer layers of the star, the cooler outer layers of the star, you get some of the light absorbed. And indeed, this whole idea of astronomical spectroscopy, where you look at the light of the sun, you look for features within the spectrum. So here's sunlight split up at all the different colors. These dark bands mark absorption by atoms and substances in the outer layers of the atmosphere of the sun. By comparison of these features to gases in the lab, the absorption lines they create, you can work out the chemical composition of the sun. And it's mostly hydrogen. So again, this is by mass. 92% is hydrogen, 7.8% is helium. And here's an interesting point. Helium was discovered first from spectra in the sun before it was discovered on Earth. Hence the name, helium, from Helios, the sun god. Only after it was discovered on the sun in 1895 was it actually found within the environment of the Earth. And then anything heavier is about 0.1% by mass. And this is the carbon, the nitrogen, the oxygen, all the heavier elements. And so the sun is mainly burning hydrogen to helium. And as I say, there's enough to sustain it for another 6 billion years. Now, we can't wind back 5 billion years and see how the sun formed, of course. What we do is, in the same way that we use our understanding of the sun to inform us about far distant stars, we can look at what's happening in the galaxy around us and use what we see to inform us to what might have happened from the sun. And we think it's a standard story, again, looking at far distant regions of the galaxy, closer spiral arms within the Milky Way. We see regions of star formation. And this is where the material that's in the interstellar medium, the cold diffuse gas, begins to collapse together under gravity. It forms colder, cooler, denser blobs. And within these blobs, small clumps, small cocoons will start to collapse under gravity. And within each of these cocoons, and maybe some of these sort of small globules here that are broken from this bigger cloud, material rains down onto the densest region. Let's say that's the center for the sake of argument. Here we have your hot cloud or your cold cloud. Materials raining down, falling under gravity. As it falls under gravity, it heats up. As material continues to amass to the center continues to heat up until it reaches temperatures, above 12 million degrees, when that nuclear fusion process can begin to start. And at that point, you've got a protostar. It takes, another few, perhaps a couple 100 million years for it to settle down and become a nice, steady main sequence, boring, dare I say it, star like our sun, with a nice planetary system around it. And it will sustain that nuclear burning for of the order of sort of 12, 15 billion years. It depends on the mass of the sun and exactly how it's turning hydrogen to helium, whether it's creating any other elements. With a star like our sun, when it runs out of the fuel in the core, it'll go through various other burning stages, swell up as a red giant, and then finally throw off its outer layers to form something called a planetary nebula that expand away, and the center collapses down to form a white dwarf, which will then cool and dim. And that will be the sort of future of our sun a long way in the future. But just to remind you, the fact that we've got hydrogen and helium as the bulk of our sun, but we've also got that smattering of heavier elements, and those are created within a supernova explosion of a much more massive star. Massive stars go through their life cycle much quickly, expand, throw off their outer layers as a supernova. They've created heavier elements in their core. There are heavier elements created within those supernova explosions, and they then get reseeded and redistributed across the interstellar medium, where they will eventually collapse into next generations of stars. So the fact that we've got that smattering of heavier elements in our sun, they've not come from nuclear processes in our sun, but nuclear processes in first generations of massive stars. So the fact that we've even got that, let alone the elements, of course, within the planets and around the sun, tells us that our sun is not a first generation star, quite feasibly second, third, generation star. Okay, so let's go back to this process of energy generation, because you've got a slight problem. You're producing all that energy in the core, and you've got to get it out of the surface. And it's not as trivial as you might think. Most of this energy is produced as gamma ray photons, and these are very energetic, they're very reactive. And they find it difficult to get very far. So just like a celebrity at a crowded party, they can't move very far before they have to undergo an interaction with someone. And it's the same for your poor gamma ray photon trying to get out of the core of the sun. You've got a highly charged plasma around it. It barely goes, a centimeter before it interacts with another particle, and that particle will store the energy and then re-emit it as another photon. And, it'll then just get passed. Again, it's like pass the parcel. You just pass the energy on, but you go in a random direction. And so your gamma ray photon leaving the center of the sun, moving out, goes slower than your average tortoise. It's about 50 centimeters an hour. And this is what's known as the radiative zone. So that goes out to about 70% of the sun's radius. And this is just this process of diffusion, okay? This gamma ray photon making its way out. And it takes of the order of 170 to 200,000 years for energy to get from the center of the sun out to the surface. It's really slow. What changes? You've got this diffusion going outwards, and then you've got this boundary where suddenly the temperature in the sun has cooled enough that you begin to get atoms. It's not all it's not all this highly charged, highly dense plasma. And atoms absorb the energy from the photons, and they hang on to it. They don't pass on the parcel. They heat up. And if things heat up, then different heat exchanges take place. And the one that's important for that outer layer of the sun is called convection. And this is a natural circulation that builds up. And it's just like if you're heating water within a pan, the movement of the water from the hot base, it heats up, it rises to the cool surface, cools down, and then it sinks back down, it's heated up. You've got that natural circulation pattern. The same thing is happening in the sun, where material goes from the hot end of the radiative zone, rises up to the surface, it loses the energy, and then it sinks back down. So that energy finally reaches the surface of the sun. And this is the disk of the sun that we see. We call it the photosphere. It's the disk that produces the light. And if you look in the light of ionized hydrogen, you begin to see a lot of details within just that sort of look away from the sunspots, just the plain disk of the sun. It has immense structure in. It has a very granular structure. And if we zoom in even further, you can see there are these cells. These are the granules. They're each about 1,000 kilometers across. And what you're seeing here are the tops of those circulation patterns. They're moving all the time. Now, this is sped up, but it gives you the sense of the sun moving and changing and oozing. And each of those marks where one of these rivers of plasma comes up, hits the surface, and then sinks back down. And they've got dark edges because, you know, again, material comes up at the center, goes out to the edge, and by then it's about 300 degrees cooler, which makes it appear slightly darker. And that's why they're ringed with those darker edges. So you've got this flow of material going all the time. And you don't just have those granules. They will move across the surface of the sun. Maybe they'll last about 20 minutes, maybe longer. They change all the time. And they are then encompassed within larger supergranules, which can be 40,000 kilometers, you know, sort of structures within structures, and they can last a few days. So the surface of the sun is constantly seething, constantly moving, and it's because of the circulation patterns under the surface. So remember, this is an electrically charged gas. You've got magnetic fields coupled to within it. So as part of this motion of coming up and then moving to the sides, you're moving magnetic field lines to the side of the granules. And in particular, those supergranules that contain, you know, thousands of these granules, you've got a net motion of the magnetic field lines getting pushed to the sides. So they've moved with the plasma, they got pushed to the sides of the cells, and then you've got much more sort of concentrated vertical magnetic field lines, which can then pull material out of the sun. So if you go just above the photosphere, we get to a region of the atmosphere called the chromasphere. Chroma meaning color. This is the pink ring that you can see within a total solar eclipse. And it's pink because it's in the light of ionized hydrogen, which is very dominantly radiates in that sort of pinky red color. And if you look at the chromasphere, you've got these long fingers of gas. They're called spicules. You just see along here, along the edge. These are just fingers of plasma that are being pulled up by the vertical magnetic fields, just, you know, for about 10 minutes, 20 minutes before they fall back down onto the surface. So here you can see how the magnetic field is dictating how the gas on the surface moves. And here's just gives you a sort of bird's eye view looking down on the surface of the sun. You can see some of this structure and this sort of striation that's involved. So you've got you've got the photosphere, then you've got the very thin layer of photosphere, thin layer of chromasphere, and at the top of the chromasphere, it's actually getting hot again. On the photosphere, I said it was about 5,780 degrees. Top of the chromasphere, it's beginning to heat up. It's about 20,000 degrees. And out beyond there, you get the corona. And the corona is what you see within a solar eclipse. It's the spectacular faint nebulosity that stretches right across the sky. Now, this is an incredibly tenuous part of the atmosphere. And again, you've got hot, charged gas. Its distribution is very much dictated by the magnetic field lines of the sun, hence these beautiful structures that you see. And it's very tenuously now held onto the sun. It's hot. It's a long way from the center of gravity. And a lot of this material is perpetually lost out towards the interplanetary space between the planets, the interplanetary medium. Now, this material you can see it very faintly invisible, only when you sort of blocked out the light of the sun, is at temperatures of 2 to 3 million degrees, which means that you can see it in the X-rays. Here's a picture of the corona of the sun, so that's the gas in the higher levels of the atmosphere in X-rays. And you see the surface of the sun is dark because it's too cold to emit X-rays. The stuff above the photosphere is so hot. And this is lost all the time from the sun. It's streaming away at a rate of about 1 billion kilograms per second. You know, again, it's no problem for the sun. It's so massive, it can afford to lose this all the time. And this is the solar wind. So we have an electrically charged plasma with magnetic fields attached that's streaming out, and it's filling the space between the planets. It's forming the interplanetary medium. It's not particularly dense. It's about 5 grams per cubic centimetre. But it has an effect, particularly on Earth, because the Earth, of course, has a magnetic field itself. It's got that sort of bar magnet, North Pole, South Pole magnetic field lines. Now, you've got all this plasma that comes out and interacts with the Earth's magnetic field, magnetosphere. So here's the solar wind, and as it, you know, this is the magnetosphere, the Earth's magnetic field sphere of influence. As the solar wind collides with the Earth's magnetosphere, it squashes it. You've got a bow shock where the two interact, and then it pulls it and elongates it out long in a sort of long teardrop away from the sun. So we are buffeted all the time by the solar wind. And actually, we're pretty lucky we've got that strong magnetic field there, because it does protect us from a lot of the harm that the solar wind could do. So this is flowing out all the time from the sun. And it fills the space between the planets. And actually, we mark this sort of theoretical boundary about the edge of the solar system, where this solar wind itself buffets up against that of the interstellar medium around it. So here's just a schematic. There's the sun. And again, we think there's the heliopause. And that's how far out the sun's magnetic field and the solar wind can actually influence before it meets and collides with the interstellar medium itself, perhaps forming a sort of bow shock. And as you may have heard, the Voyager space probes, which left Earth sort of 37 or so years ago, only now reaching the point of where this boundary between the edge of the solar system, where the sun stops influencing what goes on. It's the boundary of where the sun stops influencing its field around it, and external influences are more important. And we reckon that's about 120 times further out from the sun than the Earth is. Okay, so the question is, the sun has got this really strong magnetic field, and we reckon, I mean, as I say, it is mostly a bar magnet, okay? We reckon this comes from, there's a turbulent layer, we reckon, between the radiative diffusion zone. So this is where the light comes out by the sort of passing the parcel between all the particles in the plasma. And then you've got the convective zone. At the boundary between the two, there's a very turbulent region. You've got moving electric charges within a seed magnetic field. You end up with a dynamo action that reinforces and grows that magnetic field and perpetuates it. So this, so we're not entirely sure where the magnetic field in the sun is generated, but that's the current thinking. But nonetheless, you've got this enormously strong magnetic field. This is your generic basic structure. However, there are complications. It will be great surprise because the sun is moving all the time. So the first one is you start off with this standard configuration. And remember, the magnetic fields are lacing through these outer layers of the sun before they erupt out of the surface. But that outer layer of the surface of the sun is traveling in a weird way. And the first thing to remind you is that the center is moving more rapidly than the poles. So you get a winding up of the magnetic field. So imagine your magnetic field goes from north to south like this, and it's tracing through the atmosphere of the sun. Now the center of the sun is moving faster. And so you get a kind of mismatch, and eventually you kind of get this wrapping around and this knotting due to the differential rotation. So you've got that. And then remember, in the convection zone, you've got the vertical motion of all this plasma rising up in the currents and then settling down. So you create knots and kinks in the magnetic field. So instead of really being that very smooth bar magnet kind of field shape, the surface of the sun probably is a bit more akin to this diagram. okay? So where you've got all those knots and kinks, they break out of the surface. And this leads to a lot of the manifestations of solar activity that we study and can actually trace what's going on in the surface of the sun. Now, the one I've already hinted at that's actually the most apparent are the sunspots. Here you have dark patches on the surface of the sun. Again, be clear about the size of these. The individual sunspots can way exceed the size of the Earth. They can be the size of Jupiter. We've had one just over the last, it was probably about a month ago, biggest sunspot in about 25 years, about 200,000 kilometers across, about the size of Jupiter. These are immense structures. And they move all the time. They change shape from one day to the next. Here's a little sped up movie showing them rotating across the surface of the sun. So this is due to the sun's rotation. And you can see how they change and they evolve. And the bigger the sunspot, the longer it tends to last. Some will go once around the disk of the sun towards us. They go around the back of the sun. They'll still be there when they emerge again. So the really big sunspots groupings are like that. Now here's the most recent one that's been, again, was around the surface of the sun about a month ago, and it had re-emerged last week, but much, much smaller and much weaker. But it's a beautiful image of what a sunspot looks like. Now, the first thing is it looks dark because it's cooler. It's about 1,500 degrees cooler in the center of the sunspot. Now, if you could see that in isolation, it's still about 4,300 degrees. It's still very hot. It would be very bright and radiating. But it's just the contrast to the much hotter gas around it that makes it appear dim. It's cooler because this is where magnetic field lines erupt locally out of the surface. Again, here's a nice schematic just showing you if that's the surface of the sun. This is where they've been bunched up and knotted up, and they're coming out of the surface. And remember, how magnetic field lines behave inhibits or governs the motion of the plasma. And so the fact they're all coming out there, it's actually inhibiting the convective motion of the plasma, which would have brought heat to the surface. And so the heat isn't radiating from the surface at that point because it hasn't been brought up to there. So that's why they're cooler. And you get material around the edge of the sunspot being drawn up by these magnetic field lines. Again, here, this leads to some of that stripy penumbra that surrounds each of the really dark sunspot regions. And sunspots tend to, they come in groupings. They're very rarely seen in isolation. And within groupings, they tend to come in pairs. And the pairs are associated with a north and a south pole of the local magnetic field. So here's a grey light image of a sunspot complex. Now I'm going to show you what's known as a magnetogram, which is basically telling you the polarity, north-south, of the magnetic field associated with this sunspot. And white is north, black is south. So if you look here as I change it, all of this is north pole, this is southern pole. And this is telling you that the configuration of the magnetic field lines probably looks like this. They're erupting out of the surface through one sunspot and coming back in through another. And this idea that these are where you've got those local disturbances of the magnetic field is key to governing that structure and also the importance of this local magnetic activity and the influence it might have on Earth. The first thing it does is it gives us a reason for why the sun's outer atmosphere is so much hotter than the disk. This is sort of counterintuitive, right? Because you're generating all that heat at the core of the sun. As you move away from it, you should get cooler. There's extra energy being input to heat up the gas in the corona and in the chromasphere. And it's to do with these magnetic field lines. And the thing about magnetic field lines is they stretch. So like your elastic band, you can stretch it so far before it'll snap back into a simpler configuration. It's the same like coiling a spring. You can compress and coil a spring, and when you let it go, it'll spring back and release the energy. It's the same as magnetic fields. You can twist them up, you can kink them, you can knot them. All the time you're storing energy, and then suddenly it'll snap back to a much simpler configuration and release all that energy in one huge blast. So when you release that energy, you can send some of that as heat energy out to heat up the corona. This is what we think is providing that extra energy in the outer layers of the sun. And here, for example, we move from the disk of the sun, the photosphere, to the chromasphere, to the corona. And the hot patches in the corona are associated with directly with the location of the sunspots. So you get that direct one-to-one association. That's where the input of energy is occurring above the sunspot. But there are other ramifications for what these localized knotting of the sunspots do to the sunspot, to the whole behavior of the sun. Now, Richard Carrington, when he was observing sunspots and how they progress across the surface of the sun, noticed that with time, from one year to the next, they don't all occur in the same part of the sun. I mean, to be clear, sunspots don't just appear at random on the sun. They're confined to certain areas of latitude in the north and southern hemisphere. And as time progresses, they move closer to the center of the sun. And this is tied to a variation in the number of sunspots as well. At the bottom here, we're plotting average daily sunspot, how much the visible disk of the sun is covered by sunspots. And it undergoes a minimum, then a maximum, minimum, and maximum every 11 years. And within that 11-year cycle, this is the equator of the sun. These are the positions of the sunspots. Through that time, they migrate down towards the center of the equator. So all of this is profound for actually affecting the global magnetic field of the sun. If you remember, we've got the sunspots, we've got these kinks, these knots in the magnetic field. Those little localized knotting and kinking, they create the vertical motions, the local loops of the magnetic field, which create the sunspots. And again, as you have it looping up and down, you've got your pair of sunspots. Now, what happens is there's an ordered form of this polarity of the sunspots, in that within the sun, in the northern hemisphere, maybe you'll have all the preceding sunspots. So if the sun is rotating around this way, these will be north poles, the further ones will be south poles, and you have the opposite in the other hemisphere. What happens is you get a general migration of the leading sunspots down towards the equator, where they kind of nullify each other. And then you're left with the opposite polarity affecting the north and south poles of the global field. And so over an 11-year cycle, you get enough of this happening that these, tagging sunspots, their polarity is opposite to the main pole of that solar hemisphere. They nullify it and they change it. So the sun will undergo a cycle where the north will turn to a south pole and the south will turn to a north pole every 11 years, and then they'll flip back 11 years later. So it's actually a 22-year cycle with the poles of the sun flipping. And sometimes they don't always flip at the same time. You can have two north poles temporarily of the sun or two south poles. So again, it's fascinating to see just this interplay and how this is sustained. We undergo this variation every 22 years, or we see the manifestation in terms of the sunspots every 11 years. This is where we are at the minute, the current solar sunspot cycle. We're not going through a very standard one at the minute. It was very late starting. We've not had as many sunspots as we would expect, and we seem to be having a double maximum, which is not unheard of, but it's unusual for the second maximum to be stronger than the first, which is what's currently happening. I told you, we've just had the biggest sunspot for over 25 years in the last month, and really we should have hit solar maximum a couple of years ago. And even then, the sun really isn't as active as we would have expected. It seems a much sort of depleted maximum. So there's something about the sun where it's not quite behaving as we expect. It's quite exciting. When things don't behave as you expect, you have the possibility to learn a lot more. And we're actually tagging how the sun's behaving and seeing what the ramifications are. It could be that it's going to go through a period of quiet. There are some predictions. I mean, it's a bit like weather forecasting, right? Trying to guess what next summer's going to be like. There are predictions that actually we're going to go through a quiet phase where there are, for a number of cycles, fewer sunspots. And this is all tied to our models about the interior of the sun and the magnetic activity and how the two play together. We have gone through periods of quiet before. If you track back, so back to sort of drawings of sunspot cycles taken, as I say, from the start of telescopic observations, this is the time I referred to earlier, is when the sun went completely quiet. Not a single sunspot on the surface for 75 years. That was the Maunder minimum. There was also a Dalton minimum, which happened at the early part of the 19th century. So we know there is variation beyond that 22-year cycle. that over centuries, the sun can also change its behavior. And indeed, during that Maunder minimum, it coincided with the little ice age that happened at the time. Here's a contemporary drawing of the Thames being completely frozen over. So there are connections, perhaps with the general, perhaps on the scale of centuries, perhaps with weather conditions on Earth. It's just worth stressing, though, that we have, for over the last 40 odd years, been measuring how much energy comes from the sun to the Earth, and not just in the visible wave band, but in all wave bands. It's called the solar radiance. We measure it from telescopes up at the top of the atmosphere, so before it gets absorbed by any of the atmosphere of the Earth. And what we find is there is a slight fluctuation over the 11-year cycle. So if this is the sunspot number, this is a fluctuation in how much the radiance of the sun varies. And it's a false zero, though. Okay, that's not zero. It varies by less than 0.1% in terms of its total radiance over the cycle. This has an effect on Earth of about 0.5 to 1 degree maximum. So this is something that is taken into account with weather forecasting and with global models of climate change behavior. Now remember, out of these sunspots, you've got the vertical magnetic fields. And these can entrain and pull up the plasma and pull it right out of the surface of the sun. And when you get very active sunspot regions, they're also the places where you get things called prominences. And here's one seen against the edge of the sun, and it is, again, you've got the plasma being pulled up and pinned in place to follow the magnetic field. And just to remind you of the scale, there's the Earth for comparison. And when you see this against the edge, against space, at the edge of the sun, it appears bright. But in fact, that material is actually cooled as it's pulled up. And if you see it against the surface of the sun, it appears as dark. Okay, so you get filaments when they're seen dark against the surface of the sun, and prominences when they're seen bright. It's the same thing, material being entrained and pulled up along the magnetic field lines. And these structures are huge, and they change. Now, this is sped up by about a factor of 10. But if you have a proper solar telescope, you can observe these prominences right on the edge of the sun. And they will change on the timescale of 20 minutes, half an hour, certainly over a couple of hours. And I always find this amazing that you've got something that's several times the diameter of the sun, and yet with your own eyes you can see this changes in the shape. You can see it moving. And so the sun is very dynamic. I've told you about changes perhaps over centuries and changes over 11 years. But remember, a lot of this, very localized activity can change within minutes. So the sun, it's got levels of interest at every possible time scale. And sometimes you've got this, standard magnetic field, you've got concentration of magnetic field around the sunspots where there are local kinks. You can also have massive releases of energy. Remember, you are stretching, you're pulling the magnetic field, and it'll suddenly snap back, release energy, which will then heat the plasma around it. And this creates something called a solar flare. Here's one observed in X-rays of a very strong flare. And it'll heat the gas very locally to such temperatures it produces this flash of X-ray, gamma ray, bright white light. This is what Carrington saw, that flash of light that accompanied the solar flare when he looked at it in 1859. Now that radiation is intense, it's very energetic. It reaches the Earth within 8.5 minutes. It is, it can be dangerous. It affects our ionosphere if you have a really strong flare, which will affect communication signals, radio signals, our signals to satellites. That's the first thing that happens. It's very dangerous if you are out in space, that burst of very intense radiation. We're protected on Earth from our atmosphere, but beyond the atmosphere and at the edge of the atmosphere, you're much more vulnerable to the radiation from these flares, and you have no notice of when they might happen. And the thing that also is worrying is that when one of these flares happens, it suggests there's been this magnetic reconnection, there's been this release of energy, and sometimes they're accompanied by the expulsion of a large cloud of plasma which happens our way. So, for example, you have your prominence, it's pulled material up, it's suspended in the air, but then the magnetic field lines reconnect underneath it, and they give that surge of energy, which gives the flare, but it also accelerates and propels this material out into space. And so we see material actually being jettisoned from the surface of the sun within these flares. Again, just fountaining off the sun. Now, some of it, of course, falls back to the surface, but a lot of these ejections, the plasma then travels as a bubble through space and out into the interplanetary medium. And this is space weather. You've got the space weather, which is the general solar wind, and then you've got the space storms, which are when you've got these coronal mass ejections, they're called, these clouds that travel towards us. So here's a nice schematic. You've got your sunspots, you've got your loop magnetic field, it gets stretched, it gets pulled, it reconnects, and this plasma comes out and crosses space, and it's magnetic field and electrically charged particles within this cloud. And it crosses space, perhaps 17 hours, perhaps a couple of days, impacts on the Earth. It is going to squash the Earth's magnetic field, and you get a lot of reconnection. It only kind of pushes the Earth's magnetic field. You get reconfiguration of the magnetic fields around the outer parts of the sun and parts of the Earth. And as the magnetic fields reconnect, you can accelerate a lot of these charged particles within the solar wind and funnel them along the magnetic field lines back down to Earth. Now, this, of course, is what causes the aurora. Be clear that you've got this general stream of charged particles from the sun all the time. That's not really enough. They're not energetic enough to be funneled down our magnetic field lines. You need to give them an extra kick. You need to give them extra energy. And this comes from that reconnection event that happens when that bubble hits the Earth's atmosphere. And it's particularly noticeable if, Earth's field lines are oriented that way, and within the bubble, the field lines are oriented that way. Then you get the most release of energy that accelerates these particles most, that then all these charged particles that were in the bubble get funneled down through to where the magnetic field is most concentrated and onto the poles of the Earth. And as they hit the atmosphere, they excite the atoms within our atmosphere. This is when you get the aurorae. They're happening not so far up, from about 150 kilometers up to about 400 kilometers. This is them viewed from space, from the International Space Station, high within the atmosphere. And generally, they're confined to rings around both the north and the south poles, as shown here. But if you get one of these really explosive events, this ring expands, it goes further south. And so if you see aurorae in Cuba, Hawaii, or even Britain, then you know there's been one of these huge plasma eruptions hitting Earth, and to create those exceptional circumstances that that enlarge the ring of the aurora. But when you do get to see them, they are fantastic visions in the sky. So you've got the aurora going on all the time. They are enhanced when you have periods of great activity in the sun. Hence, when Carrington saw that flash of light and the aurora arrived within 17 hours, that very swift occurrence was because there had been a previous eruption the week before. Remember, they'd had the telegraph operator, the geomagnetic storm, and the aurora the week before. There'd already been an eruption, which had kind of cleared the path between the Earth and the sun, and then there was a second eruption, and the plasma traveled much more quickly within just a few hours, the 150 million kilometers to Earth. And this is very serious danger for us now, and it's not something that's just within the past. Most recently, about 2 years ago, there was an immense storm where, again, 2 coronal mass ejections occurred, one after another, big blasts of material off from the sun. And the first one clears the path, and then the second one then is able to expand away very quickly to hit Earth. Now, this is just a schematic where you've got the sun, a couple of solar observing space probes called Stereo A and B that watch it from different vantage points. And, we've lost it, but you also had the Earth, the position of the Earth in the movie. And what happened is it came out and was directed towards us. It didn't hit Earth, but it hit where Earth had been 9 days earlier. Okay? So that was a near miss. And our challenge is to try, okay, there's the Earth there, and it came blasted out in this direction here. So we missed it. But if one of these hits the Earth, it can be serious. First of all, you've got you can fry the electronics and all the satellites that are high up in the air. But there are also consequences on Earth. Remember those charged currents that moved along the telegraph lines during the Carrington event and the week earlier? you can still get the same thing where we now have electricity grids. We have transformers that can be strongly affected if the surges of electricity happen to choose to travel along those lines instead. So space weather and monitoring of the sun is of crucial importance nowadays. We're trying to do this prediction. You're looking, of course, for the data, shall we say, the year-to-year variation or the 11-year to 11-year variation of the sun, because it's telling us something about the fundamental inherent structure and activity of the sun. But there's also a very active industry now trying to monitor these flares. We still don't know when and where a flare is going to happen. Why does one sunspot release a flare and another one doesn't? How strong is that flare going to be? Can we know when it's going to happen? Well, at the minute, no. We don't get warning. We just know there's an active region on the sun. We don't know when it's going to snap like that. Which of these events produce the flares? How can we perhaps guess in advance that one is building up? And, can we monitor the sunspot? We can work out when a very active group might be facing towards us and release this energy towards us. All of this is part of the very sort of nitty-gritty of solar observing, and not just understanding how they might propagate out through the interplanetary medium, how fast it takes to get there, but also just trying to predict when and where these solar flares might happen and the potential damage they might do to Earth, so that we have got some warning, so that we can perhaps do preventative measures. We can shut down satellites, perhaps put them in safe mode. We can do safety measures with our transformer grids on Earth. But it's still an issue of fundamental importance, not just for astronomers, but for every one of us here in the audience today. So I hope I've convinced you there's a lot to learn about the sun, not just from physics, but just also the effect it has on the Earth. And it may be our nearest stars, but in some respect, the more we study it, the less we understand it in such detail. Thank you very much.